Hello again. We are in section 2.6, about to tackle the second objective. I guess this would be objective 2, part 1. Our second objective is to take a look at quadric surfaces. And there are several quadric surfaces we're going to focus on, and the first one is going to be the ellipsoid. So let's get started. Our ellipsoid is essentially like a three-dimensional version of our ellipse. Well, let's backtrack. Let's take a look at quadric surfaces in general. So a quadric surface is going to be a graph of a second-degree function in three variables. So we're talking about our 3D space with x, y, and z. And so the most general type of equation we're going to look at is going to be the equation where we have at most a variable raised to the second power, or two variables being multiplied together. So here's the most general type of quadric surface equation. Now, just to make things simple for us, these combinations of xy, yz, and xz are going to complicate things a little bit. They're going to rotate our quadric surfaces. So what we'll do is we'll eliminate those and just really focus on quadric surfaces that have x squared, y squared, and z squareds, and then the x, y, z. And even that, the examples that we're going to look at won't include this, because if we eliminate these pairs of xy, yz, and zx, and we still have x, y's, and z's, then those kind of shift our quadric surfaces around. So I encourage you to type in a bunch of different numbers for a, b, and c, d, e, f, g, h, i, j, and see what kind of surfaces you come up with, and vary the signs, positive, negative, and things like that, and see what happens. For this first objective, though, we're going to just take a look at the ellipsoid. And the ellipsoid in its simplest form looks like an ellipse. So this is a three-dimensional version of an ellipse, and that's going to be an ellipsoid. So we want to allow for the ellipsoid to have different ellipse-like shapes in the traces. You remember what a trace was? A trace is the intersection of the surface and one of the coordinate planes, or things that are parallel to the coordinate planes. But if we just stick to coordinate planes, then we'll see ellipses here. And of course, the special case is that when A, B, and C are all equal to each other, that's like your R, or radius, and then you have a sphere. Again, you get this equation by letting all these other terms here equal to 0. But if you include a plane X, a plane Y, and or a plane Z, then your ellipse would shift to have a different center. But for simplicity's sake, we're going to keep the center at the origin. And then again, these pairs dx, xy, yz, and zx, those things will rotate. Those things will rotate your ellipsoids. All right. So this is a general form of an ellipsoid. Again, you should look at it and say, hey, that kind of looks like the ellipse when we studied the conic sections. So let's take a look at an example and how to visualize this. All right, we have a 63x squared plus 7y squared plus 9z squared minus 63. So it doesn't quite look like our standard equation, but we can easily move things around. Let's bring this 63 over to the other side, and let's divide by 63. So in a couple of steps, we will have 63x squared plus 7y squared plus 9z squared is equal to 63. And to make this into a 1, I would get rid of this and I'll just have x squared over 1 squared if you want to put that. We have y squared over 9, because 9 goes into 63 7 times, or 7 goes into 63 9 times, plus, and then we have z squared over 7 is equal to 1. So divided out 63. This is 3 squared. So if you want to identify your A, B's, and C's, this is a 1 squared. This is a 3 squared, and this is a square root of 7 squared. So those are your A, B's, and C's. To draw this out, before we draw this in 3 dimensions, let's take a look at the pieces or the traces that are involved if we see this intersection with the different coordinate planes. So let's start with z is equal to 0. We know that when z is equal to 0, that is essentially the xy plane. And when z is equal to 0, I have x squared plus y squared over 3 squared, that's 9, is equal to 1. So on the xy plane, I would see something I would see something like this. I would cross the x-axis at plus and minus 1, and I would cross the y-axis at plus and minus 3, and then I would have this ellipse on the xy plane. Alright, now let's take a look at the yz plane, and that happens when x is equal to 0, and I would get y squared over 3 squared plus z squared over square root of 7 squared. Equals 1. And I believe square root of 7, if I look at my calculator phone, 7 square root is 2.645-ish, 2.65 approximately. So square root of 7 is about 2.65-ish. So I would draw on the YZ plane, the Y going through 3 and the Z going to about 2.65. Again, we have an ellipse, and then finally at the XZ plane or ZX plane, doesn't really matter. If you're following the right hand rule, it would be ZX, and that's when y is equal to 0, and then we have x squared plus z squared over root 7 squared is equal to 1. This time your x and your z, we have 1 and 2.65, and then it looks something like this. Alright, now what we can do is imagine trying to put all this together in 3-dimensional space. Let's see, in 3D space. So our x, our y, and our z. Really, you can just, all you really need to do is figure out the intercepts here. We have intercept at 1 and -1. -1 kind of goes behind the x, behind the yz plane. We have an intercept at y is equal to 3, so a lot wider here, -3, and then the z goes to about 2.65 and then 2.65. So we can imagine these ellipses that we would draw on the xy plane. Kind of laid out the ellipse like that along the yz plane, so that's just nice and wide, almost circular, and then the xz plane is probably the toughest to draw, and I would probably draw like this. Okay, and as you move along, you'll see these shapes change and all that stuff. So you can see it's kind of like I want to say football, but football kind of has those pointy tips, so more like a rugby ball. If you've ever seen a rugby ball, it's more like that. That's like the ellipsoid. Let's take a quick look at the graphics of this in CalcPlot 3D. Here's our ellipsoid. It actually gets cut off because of the limits, but if we zoom out, we can see the ellipsoid. Now sometimes you can kind of, because of the nature of how this is being graphed with a certain amount of losing the word, I was going to say refinement, but if we want to make it smoother, we want to be more, we have to have more cuts or more, no, I can't think of the word, but here is the cubes and axis, numbers of cubes per axis. It's the number of measurements that they do when they draw these things out. 16 is kind of not enough because we can see it's not as smooth as we would expect it to be, and so let's double that and maybe call it 32, and then that would give you a smoother looking shape. Now, because it's a lot smoother and the computer does a little bit more work to draw this out, it gets a little bit slower. So, because it has to render and re-render as you're turning this and looking at it from different points of view. So, there's a little bit of a give and take there. But here's our example of an ellipsoid. Okay.